Chapter 7: Circles, Chords, and Tangents. Now we know that a chord is a straight line joining any 2 points on the circumference of a circle. Now we start by looking at the perpendicular bisector of a chord. Consider this circle with center O. PQ is a chord. When a perpendicular bisector to PQ is constructed, it appears to pass through O. Let's see whether the perpendicular line is really a bisector. Consider a circle of radius r and center O. OA is equal to OB and is equal to the radius of the circle. AON is a right angled triangle at N. According to Pythagoras' theorem, AN squared is equal to R squared minus ON squared. BON is also a right angled triangle at N, such that NB squared is equal to R squared minus ON squared. From equations 1 and 2, we can deduce that NB squared is equal to AN squared, and therefore NB is equal to AN. And therefore, a perpendicular bisector drawn from the center of a circle to a chord bisects that chord. Or we can put it in another way, a perpendicular bisector of a chord of a circle passes through the center of the circle. Next, we look at arc length. We already know that the circumference of a circle is the perimeter of that circle. An arc is a part of the circumference of the circle. The smaller arc is called the minor arc, and the larger arc is called the major arc. In this circle, the minor arc PQ subtends an angle theta at the center. The length of the minor arc PQ is given by the formula arc length is equal to theta over 360 times 2 pi r. And so if 2 radii of a circle 7 centimeters subtend an angle of 72 degrees, then the arc length will be equal to 72 over 360 times 2 times 22 over 7 times 7, and that will give us 8.8 centimeters. Next, equal chords. In this circle, the chords AB and PQ are equal. Lines OC and OD are perpendicular to AB and PQ respectively. It has been shown that OC is equal to OD and that angle AOB is equal to angle POQ. In short, equal chords are equidistant from the center. Also, equal chords subtend equal angles at the center. For example, when a chord of 16 centimeters is drawn on a circle of radius 12 centimeters, it subtends an angle theta at the center as shown on your screen. A. Find the angle subtended by the minor arc at O, and B. Find the length of the minor arc. In our solution, AB, the chord is equal to 16 centimeters. The radius is 12 centimeters. If we mark this angle as theta, sin theta is equal to 8 over 12. And theta is equal to 41.81 degrees. We know that angle AOB is twice angle theta, that is 41.81 times 2, which will give us 83.62 degrees. And B, arc AB is equal to theta over 360 times 2 pi r, that is 83.62 over 360 times 2 times 3.142 times 12, and that gives us 17.52 centimeters. Next, internally intersecting chords. Now consider this circle on your screen. Chords A, B, and PQ intersect at M. It can be shown that QM times PM is equal to AM times BM. For example, find the length Y. In our solution, using the above convention, length CE times DE is equal to AE times BE. 3 times Y is equal to 7 times 2. Dividing both sides by 3, we get Y is equal to 4.67 centimeters. Externally intersecting chords. In this circle, AB and PQ are chords. If we extend both chords, they intersect outside the circle at S. These are called externally intersecting chords. It can be shown that BS times AS is equal to QS times PS. Notice the relationship is not similar to the one for internally intersecting chords. For example, find X. From the above, OQ times PQ is equal to MQ times NQ. 5 plus X times X is equal to 11 times 3. X squared plus 5X is equal to 33. X squared plus 5X minus 33 is equal to 0. Using the quadratic formula, X is equal to minus 8.76 or X is equal to 3.76. Distances can never be negative, and hence the answer is 3.76. We disregard the negative answer. Next, tangent and secant of a circle. A tangent is a line that touches a circle at only one point. AB is a tangent to the circle at X. A secant, on the other hand, is a line that cuts the circle at 2 points. PQ is a secant to the circle. Construction of tangents. There are two methods of constructing tangents. Method 1. Recall in Form 2, we said that any line through the center of a circle meets the tangent to the circle at 90 degrees at the point of contact. And so from a circle, draw line OA to cut the circle at B. At point B, construct a perpendicular bisector PQ. PQ is a tangent to the circle at B. Method 2. We also saw that two tangents from a common point outside the circle are equal and also subtend equal angles. And so from a circle with center O, draw line OA and mark A anywhere outside the circle. Construct a perpendicular to the line OA. Mark this point M. Now with M as the center and MO as radius, mark two arcs on the circumference of the circle, B and C. Draw the lines AB and AC. AB and AC are equal and are tangents to the circle. Let's take an example. Find the radius of the circle in this figure. In our solution, if we drew a line OB, it will bisect the angle at B, and therefore angle ABO is equal to a half of angle 30, and that is 15 degrees. We also know that the angle at A is 90 degrees. That is the angle formed between the radius and the tangent at the point of contact. And therefore, AOB is a right-angled triangle. Using trigonometric ratios, tan 15 degrees is equal to R over 8. That is opposite over adjacent. R is equal to 8 times tan 15 degrees, and that gives us 2.14 centimeters. Next, common tangents. And we start with circles touching externally. In this diagram, two circles with centers O1 and O2 touch externally at X. AB is a common tangent to both circles. The line joining their centers passes through the point of contact. Also, the distance between their centers is equal to the sum of their radii. That is, O1 O2 is equal to O1x plus XO2. Next, circles touching internally. In this diagram, we have two circles with centers O1 and O2, O1 being the center of the larger circle. The two circles touch each other internally at X. Here again, the line passing through their centers when extended will pass through the point of contact. But in this case, the distance between their centers is equal to the difference of their radii. That is, O1 O2 is equal to O1x minus O2x. Direct exterior tangents. In this figure, RS and TU are the common tangents of two non-intersecting circles with centers O1 and O2. The tangents are referred to as direct exterior tangents. Direct exterior tangents are always equal. They also form angles of 90 degrees at the point of contact with the radii of both circles. Transverse tangents. In this figure, PQ and TR are transverse tangents to the circles with centers O1 and O2 at points P, Q, T and R. We take an example. Two circles of radius 5 centimeters and 8 centimeters are such that their centers are 25 centimeters apart. Calculate the length of the tangent. In our solution, line AR is drawn to form a rectangle ARQP. ABR is a right-angled triangle. By Pythagoras' theorem, AR squared is equal to AB squared minus BR squared. That is 25 squared minus 3 squared, and AR is equal to 24.82 centimeters. AR is equal to PQ because they are the opposite sides of the rectangle, and that is also equal to 24.82 centimeters. Next, angles in alternate segments. Consider this diagram on your screen. O is the center of the circle. RS is a tangent to the circle at Q. Chord PQ divides the circle into segments A, the shaded one, and segment B, the unshaded one. Segment A is said to be alternate to angle PQS, and segment B is alternate to angle PQR. Segment A is alternate to segment B. In this rule, we have a circumscribed triangle. That tangent touches the circle at the exact same point where one vertex of the triangle is. The rule says that the angle between the tangent and one line of the triangle will be equal to the opposite interior angle of the triangle, which means this angle down here will be equal to this opposite interior angle. Just to put some numbers in there, if we had 75 degrees down here, we would automatically know that this angle here is 75 degrees. And you notice that the 75 degrees angle lines at the bottom do not touch the 75 degrees angle lines anywhere. If this is 53 degrees, you will know that this opposite interior angle is also 53 degrees. The rule is the angle between a chord and a tangent equals to the interior opposite angles in the alternate segment. Next, inscribed circles. Now, an inscribed circle is one that touches all the three sides of a triangle. Each side of the triangle is therefore tangent to the circle. The center of an inscribed circle is called the incenter of the triangle. To find this incenter, we bisect any two angles of the triangle. The point of intersection of the bisectors is the incenter. And so let's find the incenter of this triangle XYZ, and after we get it, we shall draw an inscribed circle. And so we shall construct the angle bisectors of this triangle. We start at X, we place the compass at the vertex, make an arc to cut the two including sides. We place at this intersection point and make another arc. We go down here and draw another arc. Now we join the intersection to the vertex. And that line will be the angle bisector. I can remove these arcs now to get a clear view, but you shouldn't remove yours. It's important that they remain in your diagram. And then we go to the vertex Y, place it at Y vertex, and draw the first arc. It intersects the two enclosing sides. Place the compass here and draw another arc. Do the same for this point. There is the second arc. Now take the straight edge and draw a line from the vertex to the intersection. Those two bisectors intersect at O here. This is the incenter of the triangle. If we bisect Z, the bisectors will still intersect at O. If a circle is drawn with this center, it will be an inscribed circle to this triangle. Circumscribed circle. A circumscribed circle is a circle that touches all the three vertices of a triangle. The center of such a circle is called the circumcenter of the triangle. To find the circumcenter of a triangle, we bisect any two sides. The point of intersection of the bisectors is the circumcenter. And so let's find the circumcenter of this triangle. We choose any two sides and bisect them. We start with side QR. Open the compass to more than half and draw an arc from up to down. Go to the other end without changing the compass radius and again make that arc. Now draw the perpendicular bisector to that side QR. And now we go to the other side. I will clean this up so that I can be able to see clearly, but again you should not delete yours. Side PQ, this has to be more than half. There is my arc. The other end, don't change the compass radius and make that arc. Connect those intersection points now. And with those two, we already have the circumcenter. The third side is not necessary, and even if we were to do it, it will still intersect at this same point. If this 10 is the circumcenter, this distance is equal to this one and should be equal to this one. And now we can construct the circumscribed circle. Finally, ascribed circles. An ascribed circle is one that touches the outside of one side of a triangle and the other two sides when they are extended. To construct an ascribed circle, we bisect the two exterior angles. The point of intersection of the two bisectors is the center of the ascribed circle.
The way we teach it in university and in high school as well, and colleges, is if you fall behind, you're in desperate trouble. That if you miss a class or miss an idea or don't do your homework, you go to the next class and the teacher assumes you know it, but it's like Greek to you. And so the biggest challenge is not falling behind, and the strategy is do whatever needs to be done so you don't fall behind. Seek help wherever you can find it, from students, from student help centers, from the teacher, from the teaching assistant, wherever you can get it. Because if you fall behind, it's like you're missing a floor in the building, you're missing a brick in the wall, and you just can't build the second floor without a good understanding of the first floor.